चलें जी, बिस्मिल्लाहिर्रहमानिर्रहीम. Let us start. Last time we started with the introduction of Zener diodes. We discussed the basic properties of Zener diodes. Then we presented, or then we saw the symbolic representation of the Zener diode, and along with this came the Zener diode VI characteristics. So we discussed in the characteristics that the Zener diode works either in the first quadrant when the diode is forward biased, it will work in the first quadrant, or the Zener diode will work in the third quadrant. And when the Zener diode is reverse bias, it will work in the third quadrant or the reverse bias region. And from the characteristics, we understand that in order to get Zener operation, that is to get a constant or almost constant voltage, we must ensure that a certain amount of current passes through the Zener diode, and this is called the Zener test current. So Zener test current is the current that must pass through the Zener diode, which will ensure that we are having a Zener voltage across the Zener diode. Right. After this, we discussed that although we can use the Zener diode in forward bias condition, but that is not what it is meant for. It is meant for being used in the reverse bias region. However, there will be times, for example, like in AC sine wave or square wave, where in one part of the square wave the diode is forward biased, and in the other part it is reverse biased. So that becomes okay to use. Then in the second diagram we see the Zener diode being used in the reverse bias, and only when the diode is reverse bias, only then will we get a constant Zener voltage across the load or across the Zener diode itself, right? And then came the basic circuitry for a Zener diode regulator. The basic circuitry consists of a external DC source, then limiting resistance Rs, then the Zener diode itself, and across the Zener diode we will take the load. Now for the Zener diode to operate correctly, the source voltage must always be larger than the Zener diode. The resistance Rs, which is connected in series with the Zener diode, will act as a limiting resistor. It will limit the current, and it will also ensure that IZT or the Zener test current always flows through the Zener diode, so that the Zener diode produces the required or the specified Zener voltage across the diode itself. Saw this very simple experiment where the input voltage changes, and it changes linearly, but the Zener diode, once the Zener voltage is crossed, the Zener diode produces a constant voltage without any change in the output voltage. Then came the parameters of the commonly used parameters of Zener diode, which include Vz, which is the stable Zener voltage, Iz, which is the rated current. It is the current which must flow through the Zener diode to get the required Zener output voltage. Then is the dynamic resistance, Zz, and it is the ratio of voltage change to change current across the Zener diode. It varies with the operating current. Then is the power, the rated power consumption. It is equal to the voltage of the Zener diode multiplied by the current passing through the Zener diode itself. And the temperature coefficient indicates that the properties of the Zener diode will change with temperature itself. Then we saw a data sheet for Zener diodes. Zener diodes are always determined by their model number. Each model number has specifications of its own. These specifications include the Zener voltage, the test current, the dynamic resistance, and the minimum dynamic resistance, and the current at minimum dynamic resistance. So the dynamic resistance, as seen in this practical Zener diode slide, it is the ratio of change of voltage across the diode divided by the ratio of change in Zener current. This diagram represents the practical Zener diode model. However, if we assume that there is no slope, then it takes us to the approximate model of the Zener diode. Now we are coming to our today's lecture, that is to design the series resistance RS for Zener diode regulator circuit. First, let us look at the diagram. The diagram consists of a variable power supply Vs. Then there is the series resistance RS. This series resistance RS we have to design. Then after the series resistance RS is the Zener diode itself. In this example, we are using Zener diode of model number 1N4740A, which produces 10 volts output. But this 10 volt output will only be produced if there is the required Zener test current flowing through the Zener diode itself. Only then will the Zener diode produce 10 volts. Okay. Now after the Zener diode comes the resistance RL, which is our load resistance. So to design RS, we will consider two facts. First fact is that the supply voltage Vs is much larger than the Zener voltage. This is our first requirement, that is the supply voltage must be larger than the Zener voltage. And secondly, the formula to determine RS is equal to Vs, that is the supply voltage, minus Vz, that is the Zener voltage. So Vs minus Vz divided by Zener current plus load current. So RS is equal to Vs minus Vz divided by Iz plus IL. Now let us stop over here and let us look what is this Vs, what is this Vs, what is the meaning of this Vs minus Vz. Vs minus Vz represents the voltage available across RS. So if we apply Kirchhoff's voltage law, we will recognize that Vs minus Vz, or supply voltage minus the Zener voltage for the given circuit, is equal to the voltage across RS. Now let us look at the denominator. The denominator includes two currents. First current is the Zener current and second is the load current. Now where are these two currents happening in the circuit? First let us draw the path of the Zener current, the Iz. This is the path of Iz. This is Iz. It passes through RS. It starts from the variable power supply, passes through RS, then passes through the Zener diode and returns back to the power supply. The second current IL, it passes through the power supply, it passes through the resistance RS, then it passes through the load resistance. This is IL. So this shows that through RS there are two currents passing. One is the Zener current and second is the load current. So we have to take both of these current while designing RS. Hence our formula to determine RS includes Zener current and load current. Now by definition, Iz is the Zener test current and it is the current through Zener which will guarantee the specified voltage drop across the Zener diode. So we have to maintain, or we have to ensure that Iz, the test current, definitely flows through the Zener diode in order to get the output voltage across the Zener diode. Now where the information of the required test current is, this information is normally provided by the manufacturer of the Zener diode. So in this table shown below, we have the electrical characteristics for our diode, for our Zener diode being used. We are using 1N4740A Zener diode, and here are the electrical characteristics of the Zener diode 1N4740A. That is, the first electrical characteristic is that the Vz is 10 volts. The test current Iz is 25 milliampere and the dynamic resistance is 7 ohms. So up till now only this information is enough to design RS. So to design RS, what we need is, we need the value of Vs, that is the supply voltage, and also we need the value of RL, that is the load resistance. So to design RS, let us suppose that Vs is equal to 12 volts and RL is equal to 50 ohms. Now in this formula of RS, we can find in this formula of RS, we know Vs that is 12 volts. We know VZ, that is 10 volts. And we know IZ, that is equal to 25 milliampere. But we still do not know IL, the load current. We know the load resistance, but we don't know the load current. Now, what is the value of the load current? It is very simple. The load current, the current that is flowing through the load, is equal to the voltage across the load, which is equal to Vz divided by the load resistance itself, RS. So this is IL. IL is equal to Vz divided by RL. So we can replace IL and rewrite the equation. We can replace IL with Vz over RL. And this is what we have done in this formula. That is, now RS is equal to Vs minus Vz over Zener test current plus Vz over RL. So now in this equation, we know all the values. We know Vs, we know Vz, we know Iz, we know RL. Now coming back to our design, we suppose that Vs is equal to 12 volt, RL is equal to 50 ohms. Therefore, Rs is equal to 12 minus 10. 10 represents the output of the voltage. We got the 10. We learned the value of 10 from by reading the data sheet as shown over here. So Rs is equal to 12 minus 10 divided by 225 milliampere, and this gives us a value of 9 ohms. So this means that Rs should be equal to 9 ohms. Only then we can guarantee that the output voltage will be 10 volts.
रेजिस्टेंस के होने से क्या फर्क पड़ता है? जेनर तो कांस्टेंट वोल्टेज दे रहा है ना.
Which resistance are you referring to, RS or RL?
RL.
Okay, so your question is that why do we see IL in the formula of RS? ऐसे ही है?
Yes sir.
So the question is why do we see IL in the formula of RS? The answer is quite simple. That let us look at the formula of RS over here. If we do not consider IL, then RS would be equal to Vs minus Vz over Iz. Then Rs would be equal to Vs minus Vz over Iz. But we must not forget that through Rs, there is not only one current flowing. If we do not use IL, then we are saying, in other words, we are saying that Rs is only carrying only one current, which is Iz. However, this is not the case. When we look at the circuit, when we apply Kirchhoff voltage law, or if we apply Kirchhoff's current law, we will learn that Rs is in fact delivering two types of currents, Iz and IL. So this is the first reason why we are considering Iz plus IL. The second reason is that if IL increases to a very large value, then this IL, which also flows through Rs. So this means that the voltage across Rs, that is VRS, is equal to Rs bracket IZ plus IL. So as IL increases, VRS will also increase. Correct?
Yes sir.
And when IL increases, VRS also increases. And if VRS increases, so we only have the maximum limit of Vs. So Vs will not change. And if VRS increases, then this means that voltage across Zener diode will decrease, which is not regulation. This is not what we want. So therefore, in our Rs calculation, we have to include both currents that are flowing through Rs. Does this answer your question?
Yes sir, it answered. And sir, there is another question. Sir, can we say that the Zener voltage is equal to its peak inverse voltage?
Quite. This statement is true that Zener voltage is always equal to the diode's own peak inverse voltage. Yes. Okay, now we come to the next slide. This is our next slide. The next slide is an example. This is example number this is an example number 2.24. The statement of the example is determine the reference voltages provided by the network of figure 2.109, which uses a white LED to indicate that the power is on. What is the level of current through LED and the power delivered by the power supply? How does the power absorbed by the LED compare to the 6-volt Zener diode? So let us look at the solution. We have to check that there is sufficient applied voltage to turn on the series diode elements. The white LED will have a drop of about 4 volt across it. The 6 volt and 3.3 volt Zener diodes have a total of 9.3 volt. If the forward bias silicon diode has 0.7 volt for a total and for the forward bias silicon diode has 0.7 volt for a total of 14 volt. The applied 40 volt is then sufficient to turn on the element and one hopes establishes a proper operating current. ठीक है जी. So in this example we have to determine by just looking at the we will not do any numericals right now at this stage. We will just look at the circuit and then intuitively think whether the supplied voltage of 40 volt, whether it is enough to turn on the white LED or is it insufficient. So the circuit shows, first of all, the circuit shows a 40 volt power supply. Then there is a resistance of 1.3 kilo ohm resistance. Then we see a white LED. This white LED produces a voltage drop of 4 volt when it is forward bias or when there is a certain amount of current flowing through the white LED. Then we see VZ1, which is our first Zener diode and its value, and the Zener diode value is 6 volt. Then after this we see a silicon diode. This means that this silicon diode will produce a voltage drop of 0.7 volt. And then the last component is our again a Zener diode VZ2 of value 3.3 volts. So what we can do over here is that we can accumulate the two Zener diodes. We can combine them. So let us make a same circuit again. This is our LED. This is our diode, and then comes our Zener diode, the collective Zener diode. And then the ground. The input is 40 volts. Then we have a resistance R. Then we have LED. And then we have silicon diode and a Zener diode of value 9.3 volts. So we have to determine, in order that current should pass through, we have to decide whether the required voltages of LED and the required voltage of Zener diode are being furnished or not. So 9.3 volt plus 4 volt of the LED, which gives us, so 4 volt plus 9.3 volts, which is equal to 13.3 volts. So we must have a voltage plus the 0.7 of the silicon diode plus the 0.7 volt of the silicon diode, which gives a grand total of how much voltage? 14 volts. So yes, indeed, since we are giving 40 volt, which is larger than 14, since we are giving 40 volt, which is larger than 14 volt, so um, yes, our LED will be turned on. Now comes the value of the current. What is the current passing through the resistance? So how will we find the current IL? We will find the current IL, that is IL is equal to 40 volts minus the all of the voltage drops. That is the voltage drop of the LED plus voltage drop of silicon diode plus voltage drop of 9.3 volt of the Zener, which is 14, all divided by 1.3 kilo ohms from the 1.3 kilo ohms of the R resistance R, and this will give us the required amount of current in amperes. So 40 volt minus 14 volt divided by 1.3 kilo ohms, which is equal to 0.02 amperes. So this 0.02 can also be written as equal to 20 milliampere. 20 milliampere. Right. So this was the part where the statement was what is the level of current through the LED. This was the first part. Now the second part is what is the power delivered by the power supply. What is the power delivered by the power supply? Now the second part of the question states that what is the power delivered by the power supply? The power delivered by the power supply is very simple, that PS indicates, or PS represents the power supply power, which is equal to power supply voltage multiplied by power supply current, that is IL, and this is equal to 40 volts 40 volts multiplied by 20 milliampere, and this gives us an answer of how much power? 0.8 watts. Now let us come to the third part. The third part states how does the power absorbed by the LED compare to that of the 6 volt Zener diode. So we have to find, so in this part we have to find two powers. First, power being absorbed by the white LED, and then we have to find the power absorbed by the 6 volt Zener diode. Then we have to find the power absorbed by the 6 volt Zener diode. So first let us find the power of the LED, or power being absorbed by the LED. So I will write PLED. Yes, so what will be the formula for PLED? The formula will be the same, voltage across the LED multiplied by the current through the LED, which is IL, and this is equal to voltage of the LED कितना है? What is the voltage of the LED?
4 volts.
It is 4 volts multiplied by the current. Current is 0.02 amperes, which is equal to how much watts?
0.8 watts.
4 multiplied by 0.02. So 0.08 watts. So this is the power absorbed by the LED. Now let us come to the power absorbed by the 6 volt Zener. So I will write PZ6, which represents power absorbed by the 6 volt Zener, and the voltage and the formula is PZ6 multiply is equal to PZ6 is equal to voltage across the 6 volt Zener diode multiplied by the current IL, and this is equal to 6 multiplied by 0.02 amperes. 6 volts multiply by 0.02 amperes, and this gives us an answer of 6 multiplied by 0.0. So this is equal to 0.12 watts. 0.12 watts. And in the next slide, we have the solution. In the next slide, and then in the next slide, we have the solution of example 2.24. Yes.
सर क्लियर सर 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 क्या हम ये फाइंड कर सकते हैं कि 40 वोल्ट की सप्लाई मैक्सिमम करंट कितना दे सकती है?
The 40 volt power supply is fixed volt. The resistance is constant, that is 1.3 kilo ohms. The LED has a constant internal resistance and a constant voltage drop of 4 volt. The Zener diode, the 6 volt Zener diode is constant. The silicon is also constant. So what we are looking at a very constant circuit. Therefore, the current passing through all the components of the diode will also be constant. If R was a variable resistance, in that case, we would have resolved the example for minimum and maximum resistance.
सर फिर जो पावर सप्लाई हम बनाते हैं, लेबोरेटरी पावर सप्लाई जो बाजार से आम मिल जाती है, सर उसका हम कैसे कर सकते हैं कि मैक्सिमम पावर जो है ये इतनी दे सकती है?
उसके लिए आप जो ट्रांसफार्मर आप यूज करते हैं, अगर आप 5 वोल्ट का पावर सप्लाई बनाना चाहते हैं, तो जो आप ट्रांसफार्मर यूज करेंगे जो स्टेप डाउन करता है 220 को 5 वोल्ट में, उसका जो वायर साइज होता है, द मैक्सिमम current handling capacity will be defined or will be determined or will be set by the wire size of the secondary winding of the transformer. ठीक है, तो वो जो वायर साइज होगा वो डिटरमिन करेगा कि आपका ट्रांसफार्मर कितना मैक्सिमम करंट प्रोवाइड कर सकता है, और उस करंट के बाद फिर उसकी वाइंडिंग्स डैमेज हो जाती हैं.
लेकिन सर वो तो हम ठीक है, वो वायर साइज हम कर लेंगे, सर हमें क्या पता यूजर ने कितना लोड लगाना है?
ठीक है, वो सही है. लिए फिर जो लोग बनाते हैं पावर सप्लाईज वो क्या करते हैं कि वो अपनी वायर साइज डिफाइन कर लेते हैं कि जनाब इस ट्रांसफार्मर ने मैक्सिमम आपको 10 एम्पेयर देने हैं. और अब वो बात आपकी सही है कि हमें तो नहीं पता कि यूजर ने लोड कितना कनेक्ट करना है. सो व्हाट इज द प्रैक्टिकल सॉल्यूशन? दैट वी यूज अ फ्यूज. We use a fuse. So we can use a fuse of 10 amperes. So this fuse, it will be damaged permanently when the current passing through the fuse exceeds beyond 10 amperes. अगर आपने 10 amperes पर transformer design किया हुआ है and you want that the user or the consumer should not use current more than 10 amperes, more than specified, then what we can do is that we connect a fuse in series with the transformer, so that when the current exceeds the limit, rather that the transformer should burn, let us burn the low price fuse.
सर अगर हम अपनी एग्जांपल में जो 1.3 किलो ओम की रेजिस्टेंस है, सर इसको अगर हम बढ़ाते या फिर कम करते जाएं तो हमारी पावर हमारी ज़्यादा होती जाएगी, मीन्स के 20 किलो पर आवर. तो अगर सर पावर ज़्यादा होती जाएगी तो क्या हम बार बार रेजिस्टेंस लगा के चेक करते रहेंगे कि कितनी मैक्सिमम पावर ये दे सकता है? सर ये जो रेजिस्टेंस लगी है हमारी एग्जांपल में 2.24, एग्जांपल में रेजिस्टेंस 1.3 के, सर अगर हम इस रेजिस्टेंस को कम करते जाएं, फर्स्ट क्या ये वेरिएबल रेजिस्टेंस है, कम करते जाएं तो फार्मूला 20 के ओवर आर की मदद से तो पावर तो ज्यादा होती जाएगी ना. अगर सर हम ये बार बार ये चेक ही करते रहेंगे कि मैक्सिमम कितना लोड लगाएं और लोड आगे करंट देना बंद कर दे, लोड वो सप्लाई करंट देना.
That is correct कि it is not convenient to check and recheck the value of resistance and the value of current. So the solution, there are in fact 3 solutions. First solution is that we use a fuse. When there is a fuse, we don't have to monitor any component, and we check the value of fuse. If the fuse is working fine, then the correct amount of power is being delivered. Second option is that we use some indication. If our current exceeds a provided limit, then a alarm or some indication will be turned on and we can be notified that we have exceeded the value. The third option is that we specify the resistance. We lock the resistance. आप R के सीरीज में आप जो वेरिएबल R आप इस्तेमाल कर रहे हैं उसके सीरीज में एक कांस्टेंट R भी लगा दें, so that when variable R is 0, there is always another R in series. If this R is variable, we connect another R. Let us call this R1. And R1 is a fixed resistance. So when R is set to 0 ohms, even then, because of R1, we still limit the current. So now we can safely vary R, because we have a series resistance R1. Let us say that is of 500 ohms. So now if we change our variable R even to 0 ohm, still there will be 500 ohms in the circuit and the current will be limited. This is far better than if we do not use R, and then if we don't use R and just have a variable resistance R. So when this variable resistance R turns to 0 ohm, is varied to 0 ohms, there will be too much current or infinite current. So to prevent such events, we are using a fixed resistance R.
सर करंट को लिमिट करना हमारा मकसद नहीं है, हमने तो मैक्सिमम करंट फाइंड करना है.
मैक्सिमम करंट फाइंड करना है आपने?
यस सर.
तो ठीक है, फिर आप मिनिमम रेजिस्टेंस देख लें. मिनिमम रेजिस्टेंस आपका मैक्सिमम करंट डिटरमिन कर देगा. Okay जी, so next example is 2.25. I would like all the students to read this example and perform this example, as I'm going to finish this class, and we will meet in the next class inshallah. ठीक है? So please everybody, all the class, all my students, please read from the textbook, and inshallah next time we will discuss a new article. Thank you very much. Assalamu alaikum.